find the area of this object. So if I use Wolfram Alpha, I'm getting the rows, and I can take a screenshot of these rows. They ask me to find the area, but do they want the whole thing or just one piece of it? It seems like they want the whole thing. If they want the whole thing, that means we can find 1 and multiply it by the number of petals, right? Yes, petals. Leaves, usually they call leaves, but it's a flower, so it's actually called a rose officially. It's a rose. So I count how many I have. I have 3 in each quadrant. 3 times 4 is 12. So I can multiply by 12. That is the idea. I even have a picture here somewhere. Here it is. Prepared. I just made a screenshot. I'm gonna move it here. You can quickly draw it. 3 petals per quadrant. Instead of finding them all, I just find one, but which one? And that was an amazing question that was just asked. Since we always have, no matter what a quadrant we are in, to have the angle with the positive x-axis, let's find the first one we see from the x-axis view. X-axis is your horizon, positive direction also. And the first one we see is this one. This is the first we see. The lowest one and the first in order. And the first order is counterclockwise order, is the positive direction, counterclockwise. So now I know I have 1 and 2 and 3 and blah, 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 12. And I don't need to count, that's not actually necessary. So we have 12 leaves, yes. So I will have I will find 1, so idea or solution. Let's do solution. Find the area of 1 leaf. Very confusing English. V becomes F. And then you multiply by 12 times 12. Because it's repetitive, and many objects in polar are repetitive, because that's exactly why you use polar coordinates. For repetitions, for circles, for spirals, whatever is repetitive has a period. That's the idea. Write down the formula. We just covered the formula. A is 1/2 integral from alpha to beta r squared d theta. That is the formula for the area. We need 2 angles for this leaf. 2 angles. Let me use my ruler again. Here's the first angle, and we need the second angle, and we're gonna scan from the first angle to the second angle, and we don't know those. So let me make a sketch and then show you that the sketch is wrong. This is alpha, and we're gonna scan from alpha to beta. If we scan from alpha to beta, that will be too much, right? It will be like so. That's where the R comes in. R will actually recreate the shape, and the shape is curly, like so. So angles tell me where to start and where to end. R tells me the shape, because R will be different. From this point, R is increasing, R is decreasing. R, remember, is how far away the point is from the pole, and the pole is center O. So idea is this curve, the curve passes through the pole, through GH, through the pole. The pole has equation in x and y. 0, 0 can be explained as x equals 0 and y equals 0. In polar, same idea. R equals 0 creates the pole. Because if R is 0, I'm here at the center. R is how much I did step away from the center. Well, if R is 0, we can plug it into equation we're given. We have R equals 2 sine 6 theta. So now 0 equals 2 sine 6 theta. That's what's happening here. And now we can see all the angles, all the theta that gave me 0. as the width. So the angle over here will not be the solution because r is not 0 here. Over here, no. Over here, no. Not really. Not this one, not this one. We're looking every time the curve hit back 0. So it started over here. Our radius increased, decreased, increased, decreased, increased, decreased. Hit 0, hit 0, hit 0, hit 0. And the pole is the 0. So we want to find out all those angles. And that means we don't need all of them. But actually the solution will give me all of those angles. We just need one. But if we want to find all the petals, then we can find all of these. Solve this amazing equation, which is, let's divide by 2. Then we will have, and I move sine to the left, sine 6 theta equals to 0. Use inverse functions. 6 theta equals arc sine, blah, blah, blah. Or usually people just ask the question, 6 theta equals sine. When the sine is 0? At pi, right? And it's from 0, pi, 2 pi, 3 pi, 4 pi. At pi, how to indicate all other cases? Multiply by n, where n is the counter. Pi multiplied by 0 gives you sine of 0 is 0. Pi multiplied by 1 gives you sine of pi, also 0, and so on. But we're looking for theta, not for 6 theta. So let's divide by 6. Theta is pi n over 6. That, well, usually people don't write it down like so. Pi over 6 times n, where n is the counter. All the angles being counted. And n is, let me write down here, n is 0 and 1 and 2 and 3 and 4 and blah, blah, blah. Sine at these angles give you zeros all the time. So that's where we're looking for. But we don't need infinitely many. How many do we need? Only first 2. We need only first 2. The first 2 give you alpha, and the second one give you beta. It's not the equal sign. I just want to say that alpha and beta will go from number 1 and number 2. So we just need n equals 1 and n equals 2. Not n equals 1 and n equals 2. The first n and the second n equals 0 gives you alpha, and n equals 1 gives you beta. So when n is 0, theta is pi over 6 times 0, which is 0. Where n is 1, theta is pi over 6 times 1. That is alpha and beta. So you can now finish the formula. Area of that sector, area of that first leaf of the rose is 1/2 integral from 0 to pi over 6 r squared d theta. Who knows why did I put r squared inside? It's the formula. The formula of the area. Here it is. We just need to find these two. Everything else actually is there. R squared d theta. The thing is, we don't know yet until we hit calculus 3 how to integrate r squared when integration happens in terms of theta. This is multivariable calculus. Thus, we need to rewrite r as the function of theta. Do we have it? Do we know the connection between r and theta? Go, 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 go. Yes, here it is. It's given. R is 2 sine 6 theta. So let's rewrite it. Again, in calculus 3, we're going to learn how to integrate all of this easy and faster. But first, we're introducing the idea. Equals 1/2, that's part of the formula. 0 and pi over 6, we found that. R becomes 2. Let me change the color maybe. Why everything is red anyways? Like, why so epic? Integral pi over 6. And now what's different is 2 sine 6 theta. And all of this is squared because it's part of the formula, don't forget. d theta. That is the formula that, let me write it down, area of one leaf with F. Leaf, area of one leaf. The leaf has two angles, 0 and pi over 6. And that's why I told you that this picture I'm doing with alpha and beta is not accurate because alpha actually should be horizontal. I just did not want to spoiler that. Alpha is 0, beta is pi over 6. That's where the first leaf starts and ends. And now you actually integrate, use all kind of methods we learned in this class. Starting in August, we were learning all those beautiful methods. One of them will be used right now. Actually, two of them, use substitution involved. 1/2 and 2 conveniently cancels out. Integral becomes integral from 0 to pi over 6 sine. Oh, it's not 1/2 and 2. What is it? And 4, right? So it's actually 2 squared and sine squared. I will skip this step and I will just keep 1, 2 over here. Sine squared 6 theta. D theta. So what I did is 2 should be squared and sine should be squared. Then 1/2 nicely simplifies, not cancels out, with 1/4. Actually, you don't have to do it. To be honest, I just realized that if you don't do it, the formula becomes easier. But doesn't matter. Let me ask you, how do we integrate sine squared? What do we do with sine squared? Yes? Who remembers? You remember this? We did this in exam 1. Yeah? Yes?
1 minus cosine?
1 minus cosine squared will not work. But that's a good guess.
Sine of 6 theta times sine of 6 theta?
What formula are you using? I think no. Yeah, but good guess. So we only have 2 formulas with sine or cosine square. Sine squared plus cosine squared equals 1 and double angle formula. And that's the one that will work because it will reduce the power. But good try. Good tries. And actually, usually you try and it doesn't work and you figure out something else. So we're using double angle formula. Let's kick out 2 outside from 0 to pi over 6. Sine squared is 1 minus or plus, I don't remember, right? Cosine double angle 12 theta. It's always cosine. It's not 120. It's 12 theta. Make sure this is not 0 looking. Theta is O actually with the curve. Over 2. Your job is now to remember if it's plus or minus. It's definitely cosine double angle over 2 and 1 in front. But is it plus or minus? Minus. How do you know? Because sine doesn't like cosine. Cosine likes itself, so it's plus cosine. Sine is minus cosine. That's kind of a silly way to remember. That's what helped me. D theta. Finally, we can finish after this. We had this example before. 2 now nicely cancels out with 1/2 forever. And we end up to have integral of 1. And I will skip steps right away. Integral of 1 is just theta. Minus integral of cosine is sine 12 theta. But then I'm going to divide by the leading coefficient 12. That is U sub. Perform U sub. If you don't know U sub shortcuts, I use the shortcut. And instead of plus C, we have a bar from 0 to pi over 6. Plug pi over 6 and plug 0 everywhere. It will be pi over 6 minus sine 12 times pi over 6. Actually gives you 2 pi, that is 0. So just pi over 6 left first. And then you plug 0, but 0 and 0 gives you 0. So the answer is pi over 6. One petal of the rose is only pi over 6 units. One leaf is only pi over 6 units, which is like what? 3.14 over 6, kind of 1/2. It's a little bit more than 1/2 inches. Square units squared. Remember that this is area. Units squared. So it's approximately half because pi is 3, 14, 15. half unit squared. The answer is not this. The answer will be what? By 12. Good job. Pi over 6, which will be 2 pi. What? Apparently, those leaves, even though unit squared, even though they're curled and stuff like that, they actually fill up the whole 2 pi area. 2 times pi is 3/14. So it's like 7 point something units squared. Yes? The number of leaves, we count them, but there's another way to know actually. So either you count them 1, 2, 3, 3 per quadrant, 4 quadrants times 4, 12. Or, very good question actually. So exactly in a couple of minutes I will show you this magic. The magic is this formula, r equals 2 sine theta, gives you the rows. It's a formula of the rows. Oh no, go back. Which I briefly showed in 9.3. Let me show you again. And then I will show you how you can code and control number of leaves. This is the formula of roses. This is the official term, roses. Sometimes books call them flowers. So it can have 4 leaves. It can be tilted, as you can see. See? It can be tilted and have more, even number of leaves or odd number of leaves. The cool thing is, that's why I kept Wolfram Alpha open. This number inside of sine controls the number of leaves. If 6 is an even number, if this number inside is the even number of leaves will be twice more than this number. It's part of the formula, it says here. If n is odd, then you will have the same number of leaves. If n is even, then you'll have twice more. Let's check that theory. It says if I put 5 here, I will have exactly 5 leaves, not 10. See? It is true. But we had 6, then you have to multiply by 2, it gives you 12. So knowing this formula, you don't have to count the leaves. You just know it will be twice more. Finally, I will show you why we're teaching you all of this, even though computer can do it. It's a very classical question. Why do we need to learn this if computers know everything? Because computers lie quite often. And I'll prove you right now. It's always fun to prove it with polar equations. So if I have 20 here, how many leaves do we have? Yes. 40, right? Because it's even. So I will multiply by 2. So it's going to be 40 leaves. The size of them is 2. Why? Because this number in front of it, 2, gives you the length of the radius. How far each leaf is going away from the center. Too far. So I can make them longer if I want, let's say 5. Then now they will be 5 longer. Which is not very different from the graph. Now, if I do 55, how many leaves will I have? 55, so it's odd number. So it will be 55 leaves, not 110. Now what I want to try to show you is how the computer lies, and that's why you should know. Okay, let's do 200. How many leaves is that? 400, right? Check it out. Wolfram Alpha, just like other programs, have the limit of time and space it can use when code is running. So at some point it aborts the mission, aborts the code. It says, okay, we're spending too much time calculating this. So this is the result it gives you, and this is bullshit. Look at this. Not only it has gaps, which is not correct, but they also have different heights. That means Wolfram Alpha and the code in Wolfram Alpha called Mathematica did it best to figure out 400 leaves, 5 units length for each, and draw it for you in 0.0001 second, right? And now you as engineer or physicist use this as a result, show it to people, and you will be shamed for not understanding that this is not correct. Not only the length of each leaf is different, but also there's some gaps. Computers do not handle lots of operations, so our job is to know that and fix it, or at least point it out. 400 gives you 800 leaves, so it's getting worse. And the more I put, the worse it gets. Let's do 1,000. 1,000 should give you 2,000 leaves. And it's getting worse. So it tries its best But at some point, it just stops. And that's how you know that you should know math behind of what you're doing in order to be a professional. Not all of it and not all the details, but you should be knowledgeable enough to know what is correct and what is wrong. Good job, people. Very good questions.